Hi, this is my video number 23. So in this video I'll give you a couple of examples on how to solve the homogeneous Freedom integral equation as well as non-homogeneous Freedom integral equation using the appropriate approach. One of them is that we have discussed in the previous video, Hilbert-Smith's solution. Okay, so as a first example, we solve the Freedom integral equation, homogeneous Freedom integral equation of fx equal to lambda 0 to 1 ex et ft dt. Okay, so we can write this equation as fx equal to lambda ex integrate 0 to 1 et ft dt. Then we define, let's say c equal to 0 to 1 et ft dt. Thus we have fx is equal to lambda cex, and also I can write ft is equal to lambda cet. Yeah, the reason is that we want to find c, we need to substitute those ft into the expression for t. Yeah. So if you substitute into c, substitute into c, we have we substitute into x here, into fx here, let me give you a quick number. Let's say number 1, substitute into 1, so we have lambda cex, this is equal to lambda ex, integrate 0 to 1, we have et, and ft is lambda cet dt, right? Now, of course, you can simplify that, give you we have lambda squared, we have c ex integrate 0 to 1 e to t dt. Of course, you can evaluate those things. Alright, so you can evaluate those things, and therefore what we have is that you can simplify this, ex cancel out, so we have 2 lambda c equal to lambda squared c e squared minus 1. Solve this, yeah? Solve this. Okay, now of course you can simplify this. You have 2 lambda c minus lambda squared c e squared minus 1, that equal to 0. You can factor out lambda c, that give you 2 minus lambda e squared minus 1, that equal to 0. So there are two possibilities, that the lambda equal to 0 or c equal to 0, or the other one is that this part is equal to 0, that give you lambda equal to a t over e squared minus 1. So now if we consider lambda equal to 0 and c equal to 0, so what we have is that from those, right, so let's call this number 2, yeah, then from 2 we have fx is equal to 0. Yeah, fx is equal to 0. Just we have the trivial solution. Yeah? Then if lambda different than 0 or c different than 0, then we have lambda equal to 2 over e squared minus 1. Alright, so if you substitute this into 2, then from 2 we have fx is equal to 2 c ex over e squared minus 1. Then of course we can set 2c over e squared minus 1 equal to 1. That gives you the solution of those homogeneous Fredholm integral equation as fx equal to ex. Alright, that's the first example. Now look at the second example. We want to find the eigenvalue and the corresponding function, eigenvalues, and corresponding eigenfunction of the equation, say ux is equal to fx plus lambda integrate 0 to 2 pi sine x plus t ut dt. Yeah, where given that fx is equal to x, and also find the solution. Yeah, also find the solution when lambda is not the eigenvalue, is not an eigenvalue. Okay, so we look at the solution. First we need to find the eigenvalue and the corresponding normalized eigenfunction of the homogeneous integral equation. Now we consider the corresponding homogeneous equation. Consider the homogeneous Fredholm integral equation, which is from that we have ux is equal to lambda 0 to 2 pi sine x plus t ut dt. Yeah, homogeneous means the terms here, the function here is 0. So of course sine xt you can write sine x plus t. This is sine t cos x plus cos t sine x. Yeah, therefore you can write those equation that ux is given as, so we have lambda sine x integrate 0 to 2 pi cos t ut dt plus lambda cos x integrate 0 to 2 pi sine t ut dt. Okay, so let's call this equation, let me give a name. This is equation number 1, this is equation number 2. Alright, then we define C1 as a integrate 0 to 2 pi, yeah, this part here we consider C1, this part here we consider C2. Just write it again. So we have, this is cos t ut dt, and C2 is equal to 0 to 2 pi sin t ut dt. Okay, so if you substitute into that, we have, so therefore we have, yeah, from 2 we have ux is equal to lambda c1 sin x, I think that, okay, plus lambda c2 cos x. We just change the variable. Also we can write which is when x equal to t. The reason is that we want to substitute this u into c1 and c2 so that we can find what is c1, c2. Okay, so if you substitute x equal to t, so what we have, this is ut just equal to lambda c1 sin t plus lambda c2 cos t. Then we can write c1 is equal to, because we obtain c2 here, we substitute into c1, substitute into c2. So for c1 we have that one, integrate 0 to 2 pi cos t, substitute those things, that we have lambda c1 sin t plus lambda c2 cos t dt. Okay, so what we have now, this is 0 to 2 pi, I think you can take out lambda c1, I can take out this thing, so lambda c1, so 0 to 2 pi cos t sin t dt plus this one lambda c2 integrate 0 to 2 pi cos squared t dt. Of course the cos squared t, this is half 1 plus cos 2t. Then you can evaluate those integral, yeah, you can evaluate those integral. That will give you just come up to the solution. We have, this is lambda pi c2. Okay, you can evaluate those as well using either you want to use a appropriate identity, or you can use a integration by parts. Now, which from that I can write this equation as a c1 minus lambda pi c2 equal to 0. See? So let's call this equation number 1, 2, 3. Alright, and then we can do the same for c2. Yeah, we substitute this u into c2. Yeah. We obtain c2 equal to integrate 0 to 2 pi, so we have sin t, and everything inside u is at lambda c1 sin t plus lambda c2 cos t dt. Okay, and you need to solve this equation. I mean, you need to solve those integral. Then this will give you lambda pi c1. Alright, rearrange that. That will give you lambda pi c1 minus c2 that equal to 0. This is equation number 4. So for the non-trivial solution, yeah, for the non-trivial solution, we need from 3 and 4 that the determinant of those is equal to 0. So we have 1 minus lambda pi. This one is we have lambda pi and minus 1, that equal to 0. And from here we can find what we have is this is minus 1, we have lambda, so lambda 1 is equal to 1 over pi, and lambda 2 equal to 1 minus 1 over pi. Okay. Now we need to consider both this lambda 1 and lambda 2. Yeah, for lambda 1 equal to 1 over pi. Yeah, for lambda 1 equal to 1 over pi. So we have okay, so we have C1 is equal to C2. Yeah, this is from 3. Yeah, from 3. Therefore we have therefore we have U1 x, this is equal to C1 over pi sine x plus cos x. Yeah, we obtain this from this equation here, right? So because substitute C1 C2 into equation number 2, then we have this, and we find C1 C2, then we obtain U1 as that. Okay, and then of course you can set C1 equal to C1 of pi equal to 1. Set C1 over pi equal to 1, then that we have U1x, this is equal to sine x plus cos x. Now we normalize this eigenfunction. Yeah, normalize so what we have, phi 1x is equal to U1x over integrate 0 to 2 pi U1x squared dx to the half. Okay, so if you do this, what we have, U1 is sine x cos x, sine x plus cos x over integrate 0 to 2 pi, we have square root there, sine x plus cos x squared dx to the half. Okay, so if you solve this, expand, so you got this part here, you have what, sine squared cos squared is 1, so you got 1 plus, so we have 2 sine x cos x, and then you can perform the integration accordingly. So all these things that will give you sine x plus cos x over sec 2 pi. Right? That's for lambda equal to 1 over pi. So for the lambda 1 negative 1 over pi, when lambda, which is our lambda 2, equal to minus 1 over pi, so we have C2 equal to negative C1. Then we obtain the eigenfunction, therefore the eigenfunction is u2x is equal to c1 over pi sine x minus cos x. Okay, and then again we can set c1 over pi equal to 1. Set c1 over pi equal to 1. Thus we obtain u2x equal to sine x minus cos x. Then we normalize those things. Normalize. We have phi 2x, this is equal to u2x over integrate 0 to 2 pi. We have u2x squared dx to the half. Okay, just fill up everything in there. So you have sine x minus cos x over integrate 0 to 2 pi. We have sine x minus cos x squared dx to the half. Okay, you just solve this part, and then the final answer you got sine x minus cos x over sec 2 pi. Okay, so next we need to find the what is f1 and f2. Okay, next we need to find f1 and f2. Yeah, for f1 we have integrate 0 to 2 pi fx phi 1x dx. That give you integrate 0 to 2 pi x sine x cos x over sec 2 pi dx. Again, you can solve this. I just give you the solution for that. That give you negative 1 over 2 pi. Yeah, and for f2 we have integrate 0 to 2 pi fx phi 2x dx. This is equal to integrate 0 to 2 pi. Our fx is x, our phi 2 is those things, so I can take out the 1 over sec 2 pi outside. Then what left is sine x minus cos x dx. So again, it's not difficult to find. This is, you got minus 2 pi. Alright, so that's the solution is given as we have ux is equal to fx plus lambda sum m from 1 to 1 fm over lambda m minus lambda phi mx. Okay, just fill up everything there, so that will give you x minus lambda pi sine x. Then we have 1 over 1 minus lambda pi minus 1 over 1 plus lambda pi. Okay, just substitute lambda and lambda 1 with what we have earlier. So minus lambda pi cos x 1 over 1 minus lambda pi minus 1 over 1 plus lambda pi. Okay, and then you can just simplify those things. That will give you x minus 2 lambda squared pi squared sine x over 1 minus lambda squared pi squared minus 2 lambda pi cos x over 1 minus lambda squared pi squared. Alright, so that's example number 2. I'll give you example number 3. Example number 3. Now, let's say we want to solve this non-homogeneous equation 2x plus lambda 0 to 1 sine log x ut dt. Okay, so we can write this equation as ux equal to 2x plus lambda sine log x integrate 0 to 1 ut dt. Then we define c as integrate 0 to 1 ut dt. Then we have our ux is given as 2x plus lambda c sine log x. Then also we have ut 2t plus lambda c sine log t. Okay, so then we substitute this ux and ut into those. Yeah, substitute ux and ut into that equation. So therefore we have, let's say I call this number 1 ux ut, yeah, equation number 1. C first. Then we have c is equal to integrate 0 to 1 ut, that one is 2t plus lambda c sine log t dt. Then you can evaluate this, give you 2 over 2 plus lambda. Yeah, having obtained c, so therefore our ux is given as 2x plus 2 plus lambda sine log x, provide that lambda different than minus 2. So clearly in this case, if lambda equal to minus 2, yeah, if lambda equal to minus 2, so we have no solution. Okay, so the function f equal to 2x is not orthogonal to the function sine log x. So thus the homogeneous equation contain infinite number of solution. Yeah? Thus the homogeneous equation contain infinite number of solution. Infinite number of solution. So the infinite solution, so therefore the infinite solution is given as, we have ux is equal to b sine log x, that b equal to minus 2c, because c is any constant. You can just plug in, so you have infinitely many. And the corresponding homogeneous equation for our original problem, yeah, the corresponding homogeneous equation, we have ux equal to lambda integrate 0 to 1 sine log x ut dt, has only the trivial solution, that ux equal to 0. Now we look at the example of how to find the eigenfunction for the homogeneous integrate equation. Yeah. Example, again number 4, we have find the eigenvalues and eigenfunction, corresponding eigenfunction for ux equal to lambda integrate 0 to pi kxt ut dt, where kxt is given as cos x sine t for x 0 and t, and cos t sine x for t x pi. So thus given equation can be written as, we have ux, this is equal to lambda sine x integrate 0 to pi cos t ut dt. Okay, consider this piece by piece. So substitute into there, then it can be written as that, minus lambda sine x integrate t to I think 0 to, here is 0 to x, sorry, 0 to x and x to pi sine t ut dt, right? So if you differentiate with respect to x, those equation, differentiate with respect to x, that give you u prime x, this is equal to lambda cos x integrate 0 to x cos t ut dt minus lambda something wrong here, this should be cos, okay, sorry, this one should be cos, yeah, and then we have sine x, this is plus, sorry, yeah, sine x integrate x to pi sine t ut dt. Alright, and again we differentiate again with respect to x. We have u double prime x, this is equal to we have just, if you do this, you can have those, and then that form, you can substitute into there, so you will have lambda ux minus those lambda sine x 0 to pi 0 to x, yeah, cos t ut dt plus lambda cos x integrate x to pi sine t ut dt. Okay, then you rearrange this. We have this is u double prime x minus lambda minus 1 ux that equal to 0. Okay, so now our integral equation reduced to solving this boundary differential equation. Okay? We solve the boundary value problem where u pi is 0 and u prime 0 is pi. So why we choose this pi? Because the limit of integration is 0 to pi. Then you can substitute into u. You can find those boundary condition. Now, having done that, we need to consider, of course, a couple of cases for lambda minus 1 equal to 0, positive, and as well as negative. So case 1, so let me write those things. Where is it? Okay, let me write the equation again. We have u double prime x minus lambda minus 1 ux equal to 0 with u pi equal to 0, u prime 0 equal to 0. Now case 1, when lambda minus 1 equal to 0. Yeah, in this case, if you substitute there, we have u double prime x, this is equal to 0, then the solution given as ux is equal to ax plus b. You just integrate once and then integrate twice, and then we use the boundary condition. Use the boundary condition. We have a equal to b equal to 0. That gives, so therefore we have our solution just a trivial solution for lambda equal to 1, because lambda minus 1 equal to 0, so we have lambda equal to 1. Next, we consider case 2 where lambda minus 1 is positive. Yeah. So if you consider lambda minus 1 is positive, into that, the easiest way you may put lambda minus 1 is let's say some number k squared, and when k is positive, it's always positive. You can do this. Then the solution you have ux is given as a cos set lambda minus 1 x plus b sine set lambda minus 1 x, and then we use the boundary condition. Use the boundary condition. We're going to have a equal to 0 and b equal to 0 for lambda minus 1 positive. Okay, so in this case, again, the equation has no eigenvalue. Yeah, so we can see from there the solution is, we have only trivial solution, so therefore our ux is just equal to 0. So therefore, For those two cases, we have the given integral equation. Let me write in full. Integral equation has no eigenvalue, no eigenvalues, and no eigenfunction. Alright, for lambda greater than 1. Alright, and then we need to consider the third case where lambda minus 1 less than 0. Lambda minus 1 is negative. So the solution, you have ux is given as a cos lambda square root lambda minus 1 x plus b sine square root lambda minus 1 x. And then we use the boundary condition. We get a cos lambda minus 1 pi plus b sine lambda minus 1 pi that equal to 0, and b 1 minus 1 lambda minus 1 should be lambda minus 1 that equal to 0. You got two equation here. Sorry, this is b 1 minus lambda equal to 0. Okay, for the non-trivial solution, for the non-trivial solution, so we need the determinant of those is 0. So we have cos, you can write lambda minus 1 pi sine lambda minus 1 pi, and then here we have a b 0 and 1 minus lambda. Sorry, 1 minus lambda. Okay, so we need that equal to 0. That will give you sec 1 minus lambda cos lambda minus 1 pi that equal to 0. So that's the required eigenvalues. So therefore the eigenvalue, we have lambda 1 minus lambda pi 1 lambda equal to pi over 2 plus n pi, for all n. So therefore we have a equal to 0, b equal to 0, and hence the infinite number of solution for our integral equation is given as ux equal to cos n plus 1 over 2x for lambda less than 1. Alright, and I have two more example on the how to use Hilbert-Smith's theorem, but I think I don't think I have enough time to discuss now, so probably I will consider in the next in the next video. Alright, I will make a special video for this. Alright, thank you, bye bye.